Good morning. Today we'll discuss a topic called conversion of the non-conservative form of equations to conservative form of equation. This topic comes under the subject of computational fluid dynamics for 6th semester mechanical students. Myself, I am P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Now we'll start with the conversion of this non-conservation form to conservation form for the continuity equation. In the question they may ask either conservation form to non-conservation form or non-conservation to conservation form. Anything they can be asked in the exam. So let us take up the case of non-conservation form to conservation form. Now here the conservative form which we derived from the model of flow. Okay, we have 4 models of flow, and the particular model of flow with which we got this derivation is the infinitesimal fluid element moving with the flow. Okay, the model which we considered for this derivation is infinitesimal or infinitely small fluid element moving with the flow. Okay, if we use that model, what we'll directly get is some partial differentiation form but a non-conservative form. Okay, now look into this equation. It is the substantial derivative plus substantial derivative of density rho plus rho into del dot v bar. Now what is this del dot v bar? It is a divergence of velocity. Okay, so the divergence of velocity, we have two components here, the substantial derivative of density and the rho into divergence of velocity. Now we have to convert this into the conservation form. Now how to do that? So it is having two parts, d rho by dt. First we will see d rho by dt. Now this d rho by dt, okay, this d rho by dt can be expanded like this. Okay, on what basis? We have derived in the previous classes saying that the substantial derivative, okay, or the total derivative, I will write the full form, the substantial derivative of density is equal to the partial differentiation of density with time plus u dou rho by dou x plus v dou rho by dou y plus w right here plus w dou rho by dou z. So this is the full expansion. If I write this equation in the vector notation, I will get this one. So just for the sake of reminding you, what is this del v bar dot del? Okay, we have v bar like this. V bar is equal to ui plus vj plus wk. So this is the velocity expansion. Similarly, if I want to write the expansion for del, if it is a del, I can write expansion. If it is a del rho, okay, the del rho, if it is there, how to expand that? What is the expansion? Dou rho by dou x I plus dou rho by dou y j plus dou rho by dou z k. So like this we will get. Now these two are the vector forms. If I take a dot product v dot del rho, what I will get? I will get u into dou rho by dou x, this one. Next v into dou rho by dou y, this fellow. W into dou rho by dou z, this fellow. So like this I can expand, I can get this vector form. Okay, so this will use further in the in this class will use this v dot del or del dot v many times. So what is this v dot del or del dot v? So this is a brief review of that what is v dot del. Now coming to this, what I said, it is dou rho by dou t plus v bar dot del rho. So this is the what I have written here. Okay. Now this d rho by dt is expanded like this because of the based on the substantial derivative. Now here dou rho by dou t plus v dot del rho. If I substitute this value in place of this in the first equation, what I will get? I will get dou rho by dou t plus v dot del rho plus rho into del dot v bar. So this is the equation that we are getting by substituting this in place of this in this equation. Okay. Now what is happening now? I have here two terms. Can I merge these two terms into one? Yeah. That is done by the UE rule of differentiation. Okay. UE rule of differentiation, what it says, if I write a simple differentiation duv. Okay. What I can write? I can write v du plus u dv. This is the UE rule for differentiation. Similar, the same thing I can apply here for the del, the vector notation for differentiation. Now del dot rho v bar, del dot rho v bar. This is u, this is v. If I take, then if I apply UV rule, I will get. I have to differentiate this one and this one two times. Okay. First I will differentiate with this, and this one I will multiply, and then I will differentiate with this, and this one I will multiply. So if I apply this UV rule here, what I am getting? Rho into del dot v bar plus v bar into del rho. Okay. So here what is happening? The density is outside and the differentiation is between u and del. Okay. Now here what is happening? The v bar is out. V bar is one. When v bar is there, dot product with differentiation of rho. Okay. Now if I combine this, I can write this fellow. Now if I substitute this for this in this equation, say suppose this is 1 and this is 2. So after first modification 1 became 2. Now if I substitute this in the second equation, I will get the third equation, which is our conservation form of continuity equation. Okay. So this is the conservation form of continuity equation. Now this is the first governing equation. We have two more governing equations. The other one is a momentum equation. The third one is the energy equation. So possibly we will take up the one equation in this class, that is a momentum equation. Now as I said, the approach or the model which we use here is infinitesimal fluid element moving with the flow. Okay, if I use this infinitesimal fluid element moving with flow or moving with fluid, then I will get a partial differentiation form, but which is a non-conservative form. What we desire is a conservative form. What we get is a non-conservative form. Now how to convert these three equations into conservation form or conservative form, that we will see now. Now here we have, this is one and this is the another. So left hand side, right hand side, and this is x equation, y equation and z equation. So first we will do the conversion for x form. Similarly we can write it for the other two forms also. Okay. We will take up the LHS, LHS only we have to convert into the conservation form. Now, what is this rho into du by dt? Now, du by dt is the substantial derivative of velocity. Sorry, here it is written density, it is a velocity. Velocity u. It is a substantial derivative of velocity. Now, what is rho into du by dt? Du by dt is there. Du by dt, if I expand based on the substantial derivative as we have done in the previous class, what I will get? I will write here du by dt is equal to dou u by dou t plus v bar dot del u. This we will get. Now what we have extra? We have a term which is not in a differentiation, which is outside differentiation. So if I multiply this with this density, okay, if I multiply this entire equation with density, I will get rho here, and rho here. So the same thing I have written here. This is the expansion of this rho into du by dt based on the definition of substantial derivative of velocity. Okay, it can be the substantial derivative can be of velocity, density, temperature, anything. Here what we can study is it is the velocity. Now we have two terms here. This is one term and this is another term. Just a side point. This is the local derivative and this is the convective derivative. The local derivative means at a given point with respect to change in time, what is happening to the velocity. Now here the convective derivative means between 2 points, point 1 and point 2, if the fluid is moving, what is happening to the velocity. So the combination of these two is this du by dt. What it says, when the fluid particle moves from one point to another point with respect to time, what is the total change? Okay, with respect to time, when the fluid moves from one point to another point, what is the change? Okay, so that is the total derivative. Now here we have expanded this. The same thing again we are doing. Now we have to find a alternative for this and we have to find an alternative for this. So we have here rho and u. Okay, rho and u is there. What is the UV rule for dou by dou t of rho u? Okay, we have rho u. That is the reason we are taking dou by dou t of rho u. Now, if I apply the UV rule for this rho u, what I will get is rho into dou u by dou t plus u into dou rho by dou t. Okay. Now, if I take this fellow the other side, okay, if I take this fellow on the other side, what I will get? I will get the equation for rho into dou u by dou t. This is what we need. So this rho into dou u by dou t is equal to dou by dou t of rho u minus u in dou rho by dou t. So this is the one equation we got. So what is the second term? The second term is rho into v bar dot del u. Now, is there any other UV rule applied for this? Okay, here I have the v bar, rho and u. Rho v bar one term and u another term. For these two, I have to apply the UV rule. Now, del dot rho u v bar. Okay, what are the two terms here? Rho v bar and u, two terms. So, rho v bar one term and u is the other term. Now, if I apply the partial UV rule for this, what I will get? I will get rho u bar. One time I have to differentiate and multiply with u. That is what I have done here. U into del dot rho v bar. The second time what I have to do? I have to take a differentiation of u, that is del u, and multiply with rho v bar. Rho v bar dot del u. So this is the UE rule applied for rho u v bar. Now what we need is rho into rho v bar dot del u. So here, is there any that term? Yeah, I have this term. So this is what we need, rho v bar into del u. So what I have to do, I have to take this term that side. So if I take this term that side, what I will get is rho v bar dot del u is equal to del dot rho u v bar minus u del u into del dot rho v bar, u into del dot rho v bar. This is what we are getting. So we have two terms here. One is this term, and the equivalent value of this is this, and the other one is this term, the equivalent value of this is this. So if I put this 1 and 2 in this equation, what I will get? I will get this rho into du by dt is equal to rho dou by dou t of rho u minus u into dou rho by dou t. Okay, minus what I have previously, I have u into del dot rho v bar plus del dot rho u v bar. So this is the, I did not do anything. I have substituted. I got two equivalents for the substantial derivative of the terms in the substantial derivative of du by dt. I substituted those two equivalents into this the expansion of the substantial derivative. So if I do this, what is happening here? I have two terms here. One is u into dou rho by dou t minus u into del dot rho v bar. If I take u outside common, I am taking u common. What is happening is I will get in a bracket dou rho by dou t plus del dot rho v bar. Now what is this term? It is looking like somewhere we have seen this. Now this is nothing but our continuity equation, the first derivation that we have seen. Now what is this? This is equal to 0. By continuity equation, this entire term is equal to 0. So if I put 0 here, what I will get? Rho into du by dt equal to dou by dou t of rho u plus del dot rho u v bar. Okay, so this is what is the simplification for this LHS of the momentum equation for x direction. So if I put this in our momentum equation, what I will get is this one. So this dou by dou t of rho u plus del dot rho u v bar equal to minus this. This we are not changing. We have changed only this one so that we got a del dot sum term. So del dot sum factor we have. So this equation is called the conservation form of momentum equation. Now the conservation form of momentum equation we got in x direction. Similarly, what I can do, I can write this in y direction and z direction. So what is the changing here? Y direction velocity is u. In place of u, I will get v, and here this is the term which is decided by the direction. In place of u, I will get v bar. Now the other side, the pressure differentiation with x, here y direction pressure differentiation with y, and now here dou by dou x of tau xx. Okay, the stress in x direction and changing in x direction, this is a normal stress. The tau in x direction but changing in y direction, so it is a shear stress. Tau in x direction but changing in y direction, so this is a shear stress. It is changing in z direction, so I differentiated with z. It is changing in y direction, so I have differentiated with y. Similarly, this is the body force, the component of body force in x direction, so it is Fx, rho into Fx I got. Now what I have to do here, I have to put the y components here. So the pressure differentiated with y bar. So then x, it is direct acting in y direction and changing in x direction. So differentiation with x, it is acting in y direction and changing in y direction. So it is normal stress differentiation with y bar. So it is acting in y direction and changing in z direction. So partial differentiation with respect to z. So the common is, all these are acting in y direction but changing in x, y, z different directions. And this fellow is the component of the body force per unit mass in the y direction. Now this one, the partial differentiation of pressure with respect to z, and this is acting in the stress acting in z direction and varying in x direction. So it is differentiated with x, and it is acting in z direction and varying in y direction. So I differentiated with y. This is acting in z direction and varying in z direction. So I differentiated with z. So in all the three cases, if you see how to easily remember this stress, this stress, this stress, all the three stresses are acting in x direction. So the second term is x. So what is the first one? It is varying in x direction, varying in y direction, varying in z direction. Varying in x direction, differentiate with x. Varying in y direction, differentiate with y. Varying in z direction, we differentiate with z. Similarly, if I see here, all are acting in y direction. So the second suffix here, it is y. Now what is the first suffix showing? It is x, y, z. Varying in x direction, varying in y direction, varying in z direction. Varying in x direction, so differentiation with x. Varying in y direction, so differentiation with y. Varying in z direction, so differentiation with z. So the third one is same again. If you say all are acting in z direction. Now the first one is varying in x direction, so differentiation with x. Varying in y direction, so differentiation with y. And varying in z direction, so differentiation with z. So this is about the conservation form of momentum equation. Now these momentum equations are also called the Newton's Navier-Stokes equation. Okay, these are also called Navier-Stokes equation. How to convert this momentum equation into Navier-Stokes equation? Now we have the Newton's second law of viscosity. Okay, we have, what is that? Newton's second law of viscosity. What this Newton's second law of viscosity states? It states that the stress is directly proportional to the velocity gradient. Okay, tau xy or tau yx, both are magnitude wise it is same, but they are acting in different directions. So the tau xy is equal to tau yx. Both are magnitude wise it is same, but acting in different directions. So we are talking about magnitude here. That's why these two values are equal, and that is equal to, what is this? The velocity gradient. Okay, so suppose this is a u velocity. How u is varying in y direction? Okay, the velocity u varying in y direction. So it is dou u by dou y. Similarly, the v velocity, how it is changing in x direction. So v velocity changing in x direction. How to write? It is dou v by dou x. So the velocity, u velocity is changing in y direction and v velocity is changing in z direction, x direction. So that is giving us the shear stress xy and shear stress yx. Similarly, the shear stress xz and zx. So the u velocity is changing in z direction and z velocity is changing in x direction. Okay, x velocity is changing in z direction, Z velocity is changing in x direction. So because of these two, what I am getting is xz and zx. So what is zy and yz? Zy and yz. Now the z velocity is changing in y direction and y velocity is changing in z direction. So z velocity is w, it is changing in y direction, and y velocity is v, it is changing in z direction. So because of this, we are getting this shear stress. So what this Newton's law states, it is the shear stress is proportional to the velocity gradient. Now we said proportional. So proportional means there must be a constant of proportionality to make it equal. So the constant of proportionality is mu. It is called the viscosity. It is called the dynamic viscosity. Okay, this is the dynamic viscosity. It is the constant of proportionality for the Newton's law of viscosity. Now this is about the shear stresses. Now what about the normal stresses? Are they related to this velocity gradient? Yeah. So here this Stokes, okay, a scientist called Stokes, he made a hypothesis saying that lambda is equal to minus 2 by 3 mu. Okay, lambda is equal to minus 2 by 3 mu. Now what is this lambda and what is this mu? Lambda is nothing but the bulk viscosity and mu is the molecular viscosity. Okay, molecular viscosity and bulk viscosity. What is the meaning of molecular viscosity? The molecular viscosity means layer by layer. If there is a friction or if there is a resistance for one layer over the other layer, then it is called the molecular viscosity. Then the what is bulk viscosity? It is because of the bulk movement of the fluid. Okay, the fluid particles, they want to have a so suppose this is x direction. The bulk motion of this fluid particles in x direction, they are opposed by some stress called normal stress, and that is proportional to the. So here you can see u and x and y. Okay, and here x and y, here also y and x, but here this is resulting in this is the resultant of the molecular viscosity. Okay, so this is the two layers are like this, one layer is going the other layer. Okay, one layer is going on the other layer. Because of this, the friction between these two, this is because of the viscosity, the viscous friction between these two is resulting into the normal stresses. Now what is this shear stresses? Now what is this normal stress? So the normal stress is acting like this. Now what is this? The bulk, the as a bulk as a bulk of the bulk motion of the fluid, if it is resisting, then it is resisted by this normal stress. Okay, this resistance is giving rise to normal stress, and this is generally because of this dou u by dou x, the velocity gradient in normal direction. Okay, u velocity in x direction, x velocity in x direction, y velocity in y direction, z velocity in z direction. Because of this, I am getting this normal stress. In addition to that, what I have is the term lambda into del dot v bar, lambda into del dot v bar, lambda into del dot v bar. So this is common in all these three the normal stresses. So these are the 6 stresses we have based on the Newton's law of viscosity. What this Newton's law of viscosity states? It is states that the stress is proportional to the velocity gradient. Okay, stress is proportional to strain, and the strain is nothing but the velocity gradient here in this case. Okay, now if I substitute these 6 stresses in the previous equation, what I will get is, I will get like this. Okay, so what we have written here is, this is this can be written like this also, rho u plus del dot rho u v bar, and here it is del rho v by dou t plus del dot rho v v bar, and this one is del dot rho w v bar. So this is what we have written in the previous slide. So if I expand this, I will get this one. What is this? Del dot rho u v bar. U is common, rho is common. What is changing is, with x I will get u, with y I will get v, with z I will get a w. Similarly here, rho v is common. Rho v is common. With x I will get u, with y I will get v, with z I will get a w. Now here rho w is common in all the three. With x I will get additional u, with y I will get additional v, with z I will get additional w. So this is about the left hand side. So the left hand side we have not changed anything. What we changed is here previously I have tau xx. In place of tau xx, I placed the equivalent value based on the Newton's law of viscosity, and here I had tau yx. Okay, I had tau yx in the momentum equation based on the Newton's law of viscosity. The equivalent term is placed here, and here what I had is a tau zx. In place of tau zx, I placed the equivalent value of that. So this form of equation is given by two famous scientists. They are known as Navier and Stokes. In their name, these equations are termed as Navier-Stokes equations. So this is about the Navier-Stokes equation. So what we have seen in this class today, one is the conversion of non-conservation form to a conservation form of continuity equation, conservation form of the non-conservation form of momentum equation is converted to conservation form of momentum equation. And what we did, we applied the Newton's second law of viscosity and substituted the stresses in terms of the velocity gradient and made the momentum equations to the Navier-Stokes equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.